Okay, this video is going to look at the gas law relationships between a bunch of different quantities. But to back up, let's do a little revision of some underlying ideas and units that are going to be important. Okay, so there's going to be two types of relationships that we see in these gas law relationships, one of which is directly proportional relationships and the other of which is called inversely proportional. Or I've seen on the IB they get mad if you include proportional, so we might just say an inverse relationship. So just to be extra careful, I'm going to cross that out and call it an inverse relationship. When you have a directly proportional relationship, that means that as some quantity x changes, then y will change by the same degree or the same factor. So if x doubles, y doubles. If x halves, then y halves. If you multiply x by 10, y multiplies by 10. And so a directly proportional relationship looks like that, if you see it on a graph. So they change together. In an inverse relationship, when one quantity doubles, the other one halves. So if you think of, let's pick a random point and we say 1 and 1. So if we started off and both values were 1, when I double x, so I go out to 2x, then y should go down to 1/2, and so I should be here. And if I go to half x, then I should go to 2y, so I should go here. And if I go to 4x, then I should go to a quarter y, so it'd be about there. And if I go to a quarter x, I'd go to 4y. So this, you can start to see, will give us a shape that is a curve. So an inverse relationship, they often try to see if you know this shape. They kind of try to trick you, and they'll give you ones like this, and they'll say, is this an inverse relationship? And the answer is no. That's negative linear. That's different than inverse. Inverse takes this curve shape, so be on the lookout for that. So that's a little bit of the background knowledge we need for the gas laws. The other things that we need are some of our units, particularly units of temperature and of pressure. So temperature is a measure of, temperature is a measure of the average kinetic energy of particles. So it's proportional to kinetic energy of particles. So if this is temp in Kelvin, we're going to come back to that, then this is kinetic energy or average kinetic energy of particles, and they go up proportionally. Okay, that's a directly proportional relationship. That's the definition of temperature. Okay, now most people in the world use the Celsius system to keep track of temperatures, and it's based on water, where 0 degrees is defined by the freezing point of water and 100 by the boiling point of water at sea level. And then the difference is just divided up into 100 degrees, and that's how big a degree Celsius is. So that's great. That's quite useful, except that in calculations, it doesn't make sense to have negative temperatures, because what we just said is that temperature is a measure of kinetic energy. So when you cool something off, it can't really have negative kinetic energy. It can have less kinetic energy. As you cool something off, you'll slow down its particles, and so kinetic energy goes down, but it doesn't really become negative. Negative kinetic energy doesn't make a lot of sense. So looking at the negative part of the scale is going to be problematic when we try to use temperatures in calculations. So what they did was they came up with a different temperature scale that is the same size as the degrees Celsius, but the starting point of the Kelvin scale is 0. So it turns out that there is an actual lowest possible temperature. Absolute 0 is what it's called. This is where all particle motion would stop. If all particle motion stops, there's no kinetic energy, therefore there's no temperature. And so you can calculate that value. Even in our lab, we could calculate this value fairly accurately to be negative 273 degrees Celsius. So what they did was they said, all right, well, that temperature is the new 0. Since it's the lowest possible, that will be our 0 point. But then the way that kelvins change is the same as the way degrees Celsius changes. So this is a change in temperature of 273 degrees Celsius. So that same change is also a change in temp of 273 kelvins. Notice that kelvins are not degrees Kelvin, they are just kelvins, but they are the same size. So when you look at change in temperature, it actually doesn't matter if you're in Celsius or Kelvin, the change is the same. But when you're talking about actual temperature values, individual temperature values, you can see that the Kelvin value is always 273 higher than the corresponding Celsius value. So if it's 0 degrees Celsius, it is 273 Kelvin. That value, 0 degrees Celsius and 273 Kelvin, is known as standard temperature. So when scientists, chemists, physicists want to compare things, they need to know that they were done under the same conditions. So they come up with certain temperatures where they will sort of define things, the standard values for things. And so one of those standard temperatures is 0 degrees Celsius. Another one that's called standard ambient temperature, because standard temperature is pretty cold. 0 Celsius is a pretty cold temperature. 25 degrees Celsius or 298 Kelvin is another sort of standard that gets used sometimes. So be on the lookout for those two terms. They will be used, and those values are in the data booklet for you to reference. Okay, let me come back to this. Yeah, okay, so here's something that they'll also bring up, and this will be relevant in these gas law equations. Sometimes they're going to talk to you about temperature being doubled. And what they're trying to catch you on is if you say the temperature of something is 27 Celsius, your instinct will tell you to multiply it by 2 and go to 54. But that's not actually doubling the kinetic energy because the Celsius scale doesn't start at 0 like it should. So in order to double something's temperature, you have to convert it into Kelvin first. So 273 plus 27 is 300 Kelvin. So to actually double something's temperature that was at 27 Celsius, you would need to increase its temperature until it got to 600 Kelvin. And then if I want to go back into Celsius, I subtract 273, so I would get 327 Celsius. So to double something's temperature is often a huge temperature increase, something that we wouldn't see in our lab, because if we're around 20 degrees Celsius, you would have to heat something up to over 300 degrees Celsius in order to truly double its temperature, okay? And if we want a half temperature, same thing. Any of these calculations on temperature, we need to be in Kelvin. So having a temperature, so times a half, would be 150 Kelvin, and then we would subtract 273 from that, and so we would get minus 23. Okay, am I right? I think I'm right. Okay, that would be the degrees Celsius, okay? So all calculations in temperature must be done in the unit of Kelvin, so get comfortable with that value, that conversion. Okay, then the other unit that's probably new for us is the unit of pressure. So pressure is force divided by area. The SI unit of pressure comes from the SI unit of force, the Newton, spread out over the SI unit of area, which is a meter squared, and you get something called the Pascal, which is a certain amount of pressure, PA. But a Pascal is pretty small. The atmospheric pressure at sea level is around 100,000 pascals. So 1 times 10 to the 5 pascals, which is kind of an annoyingly large number to use in our calculations. So instead of using pascals, we usually use kilopascals. So a kilopascal is 1,000 pascals. So normal pressure is 1 times 10 to the 2 kilopascals, or 100 kilopascals. So we're typically going to use kilopascals in our calculations for gas laws. And so pressure is all about these collisions of particles, and it's about putting force, putting pressure, squeezing gases or unsqueezing gases by giving them more space to move around in. Okay, so we have our relationships. We're looking for direct and inversely proportional relationships. So there are basically 4 relationships that are really important. Okay, the first of which is pressure and volume. This is also known as Boyle's law, but you don't need to know the names in the chemistry syllabus. So if we assume that we keep the amount of gas the same, so we aren't messing with the moles of gas, the particles of gas are the same, and the temperature is the same. If I squeeze on a gas, so if I increase the pressure, then I would expect that the volume goes down and vice versa. So this is an example of an inverse relationship. So we would expect the graph to look like a curve somehow, like this. That would be the pressure-volume relationship. So this is inverse. And when you have an inverse relationship, you can say that pressure times volume will be proportional to some constant. That means as pressure goes up, the volume has to go down by the same amount in order for them still to equal the same value. It can also be written like this: P1 V1 equals P2 V2. So this is Boyle's law in an equation. As pressure goes up, volume has to go down by the same factor. You can rewrite this graph. You can rework this graph. So before, if the volume was 1 and then we change the pressure to 200, that's doubling the pressure. We should half the volume, half it again. In this one, we halved the pressure, so we should double the volume, and we get that curve. Okay, now if we have these pressure values, and I do 1 over the pressure, if I inverse the pressure value, this relationship we said was an inverse relationship. So if I invert the pressure values, I'll end up linearizing my data. Let's see, what is 1 over 1? 1. What's 1 over 2? 1/2. What's 1 over 4? 1/4. What's 1 over a half? 2. And we said that these volume values, you can see them up above, are 1/2, 1/4, and 2. So if I rewrite this graph, and instead of graphing pressure and volume, I graph 1 over pressure and volume, I take my inverse relationship and I make it linear. Not such an important idea in chemistry, but I have seen them present this graph before and try to evaluate if it's correct or not. So just to show you that. Okay, so we've seen the pressure and the volume thing. I'm going to go on to another gas law so that this video doesn't go on forever. If I warm up a gas, then the particles have more kinetic energy, they move around faster, and if the container is flexible, like a balloon, then the volume of that gas will expand. So as the temperature of a gas goes up, so does its volume, assuming that the pressure is constant and the amount of gas is constant. So warm things expand and cool things contract. So this is a directly proportional relationship. When we write this as a gas law, we would say V1 over T1 equals V2 over T2. So if you increase the temperature, then this volume will also have to go up by the same amount in order for this equation to still equal each other before and after the change. A directly proportional relationship should give us a linear, directly proportional line where they increase together. And remember, we're talking about temperatures in kelvins here. Okay, third gas law has to do with temperature and pressure with the volume being held constant. So now you have a fixed container that's sealed and doesn't change in size, and the amount of gas isn't changing either. So now as I warm up my gas, the particles move around a lot more, and they collide with the walls of the container a lot more, and therefore that creates a lot more pressure on the inside of the container. So that's a directly proportional relationship. This is why you don't throw pressurized canisters into fires. As they get hot, they will eventually explode. Very dangerous. Okay, so this is going to look a lot like our previous equation, volume over temperature, to show the direct relationship. So we're going to see we have pressure over temperature to show this direct relationship. So P1 over T1 equals P2 over T2. Same idea. If you make a change in one, then the other will have to change by the same amount in order for these things still to be equal. And direct relationships look like that. Okay, our final one has to do with moles and volume. This is known as Avogadro's law. And the concept is that, and this is where why Avogadro, his name was given to the number for the mole. His idea was that equal volumes of gas contain equal numbers of particles. So if you have a balloon of helium, and you have a balloon of ammonia gas, and you have a balloon of oxygen gas, they all contain the same number of particles. It doesn't matter what the gas is. Remember that when we have ideal gases, we assume that the particle size doesn't matter. So the fact that it's helium versus O2 does not change how much space it will take up. It does change how heavy it is. A helium balloon with 1 mole in it only weighs 4 grams, whereas one with oxygen, it weighs 32 grams. So a helium balloon will float and an oxygen balloon will sink, but the number of particles are equal. Now, if you put more moles into a balloon, like if you blow a second breath into a balloon, you know that it gets bigger. So as you increase the number of particles or the number of moles, then naturally the volume of that gas also increases, assuming you're keeping everything else constant. So once again, we have another directly proportional relationship, and directly proportional relationships can be written like this. So this just says whatever I do to the number of moles of a gas, I will also do that same thing to its volume, increasing or decreasing. And so we're going to get that relationship again, a linear one. Okay. If I skip ahead, if we take all 4 of those laws about pressure and volume and temperature, pressure and temperature, volume and moles, and we combine them together, we essentially get 2 different giant equations. This one here, although this one is often written without the moles in it, when you keep the amount of gas the same, this one here is called the combined gas law. And so it allows you to do calculations when you change more than one thing. So if you were to change both temperature and pressure, for example, you could solve for what happens to the volume. So this is called the combined gas law. It's in the data booklet. And it also gives us the ideal gas law. So if we have that the pressure one, PV over NT, and that's equal to P2 and V2 and N2 and T2 and so on. So this is always equaling a constant value. We've got all the values we can have for a gas. We've got its pressure, its volume, its moles, and its temperature. If those are always being plugged into this equation and they're always equaling the same thing, then we get a constant. And this is the ideal gas law constant, or just the gas constant. This is how we usually write the ideal gas law. PV equals nRT. P stands for pressure, V stands for volume, N for moles, T for temperature in Kelvin, and R is the gas constant, which equals 8.31 joules per Kelvin per mole, or it has the units of pressure, volume, moles, and Kelvin. That equation is very nice because if we know 3 values about a gas, like its pressure, volume, and temperature, we can work out what the moles must be. Or if we know the moles and the temperature and the pressure, we can work out what the volume must be. So it allows you to solve for other values about a gas. So we have 4 gas laws, individual gas relationships about these different quantities. We have kelvins and kilopascals as our new units, and we can combine all the individual gas laws into the combined gas law and the ideal gas law, and that lets us solve problems, do calculations about ideal gases.